Okay, so we'll talk about refinements of the Borromean obstructions, and so we saw in the previous lectures a few examples of varieties for which the Borromean obstruction to the Hasse principle or to weak approximation was the only one. But we also mentioned the example by Skorobogatov of a surface, a smooth projective surface of a Q, for which the Borromean obstruction to the Hasse principle is not the only one. So we'll introduce methods in this lecture to try to understand these examples. So we need to define something, so idea. Define subsets of the adelic points, say some obstruction subset that contains at least the rational points and eventually the closure of the rational points. And we would like these subsets to be contained in the Borromean subset, so that it could be possible that this one is non-empty, but the emptiness of this one is explained by the emptiness of this one. So this is the idea of what we are trying to define. And to do this, we will use torsors over X. So in the first subsection, I will need to give a few notions about torsors over an arbitrary base, and twist by torsors. So let's start with the definition. So let say S be a scheme, and G say a sheaf in groups for the, well, you can choose your favorite topology here. The best topology to consider in general is the FPPF topology, but in fact, in our situation, we will restrict to smooth group schemes G, so étale topology will be enough. You take such a sheaf for the étale topology, say, and I need to define what a torsor under G is over S. So the definition is really a natural generalization of the one we gave for torsors over a field. So S torsor under G is a sheaf for the same topology. Let's call it, I don't know, X, with a oh yes, I am defining a right torsor. So I will need a right action. So you ask, you want an action of G on X, so satisfying the axioms you can imagine, so that it is a group action. And we will need the condition, the analogous condition we gave over a field. So we put two assumptions. The first one is that the natural morphism that we considered in the case of fields, so given by this, so I denote with the dot the group action. So this morphism is an isomorphism of sheaves.
Is X also a sheaf in the FBBF topology?
Yes, well, you do take the same topology as here. Okay. So if you put FPPF
over S.
Over S, yes, sorry, yeah. Everything is over S, and you choose one topology, and all sheaves are chosen for this topology. So this is an isomorphism of sheaves, and the second point. So this exactly means that the action is free and transitive. And you also need to add a second condition saying that X is non-empty in some sense. Because if X is empty, the first condition will be satisfied. But we don't want to take this case into account. And here non-empty will mean locally non-empty for the topology we have chosen. So over a field, we ask the existence of a point over the separable or algebraic closure if in characteristic 0. And here, so we ask for the existence of points, of sections of the sheaf X locally for the given topology. So there exists a covering, say SI, for the chosen topology, so either FPPF or et al., such that for all I, the set of sections of this sheaf over SI is non-empty. Okay? And as in the case of field, you can deduce immediately from this definition that a torsor X is locally isomorphic to the group G itself. And so I don't write it, but of course, if S is spec K and G is an algebraic group, then you recover the same notion as before. Yeah, because before we ask the torsors to be varieties, and but in fact, if you take a sheaf satisfying these conditions over spec K, it is representable by a variety. Okay, so this is really a natural generalization. So of course there is a notion of morphism, which I won't define. Morphism of torsors, and also a notion of any morphism will be an isomorphism, as in the case of fields, and as in the case of field, given a point X, as soon as your torsor has a point, then it is isomorphic to, so such a point defines an isomorphism, get an isomorphism of torsors between X, in the other direction maybe, between G and X. So this is the trivial torsors, as in the case of field, with the action on the right by translation. And you can consider the map defined by the action on the given point X. This map is an isomorphism of torsors. Okay? So since you have points locally, locally for the FPPF orbital topology, you have such isomorphisms. Okay. And this, so this is called a trivialization of the torsor. And exactly as in the case of field, you have the following proposition no, before giving the proposition, I have to give the definition of the object appearing in the proposition. So definition. So I will define the H1 of G in this setting. So we define H1 of X G to be the set of isomorphism classes of torsors. Of S, it was XS, I think, of S torsors under G. And similarly, as in the case of field, we have a cocycle description of this cohomology of this set, given by Čech cocycles. Sorry. So I have to take a covering of S. I define the set of cocycles associated to this covering. So this is a set of 1 cocycles, the Čech 1 cocycles. Modulo equivalence. So let me define what it means here. Where U is a collection of maps Si to S is covering. So for instance, a collection of étal morphisms covering S, and a 1 cocycle is a family. So you take sections, say G, I, J. So if this is indexed by a set I, so you take a family of elements in this one here means Sij means the intersection of Si and Sj, well, which means the fiber product in this setting. Okay, so you take a collection of section of the group over these intersections. So this is a well, and you want this collection to satisfy a cocycle condition, satisfying. So you remember the cocycle condition we gave in Galois cohomology, in non-abelian Galois cohomology? Then you just have to generalize it to this setting. And the condition now writes something like Gi. So for all I, J, K, something like Gi, K equals Gi, J times G, J, K over in okay, you can intersect the 3 Si, Sj, Sk, and you ask for this compactibility condition, which is really the analog of the condition of the cocycle condition in the Galois setting. No, is this really what I want? Yes, I think so. Okay. Yes? Yes. I don't define the equivalence relation, but this is a generalization of the one we defined in Galois cohomology. Okay? So we have two H1s, and we have the same comparison result as in Galois cohomology, which is the following proposition, which I won't prove. These two H1s are isomorphic if you take the limit over all coverings U. Yes, H1SG is canonically isomorphic to the limit over all coverings U of the H1 Czech of U G. And the proof is exactly the same as in Galois cohomology. You fix a torsor, you trivialize it locally, so you choose points locally, and then you have so you can identify the torsor locally with G, and you look at the intersection of the cover that trivialize your torsor. That's how you construct the Gij, comparing the 2 points you have chosen, the one on Si and the one on Sj, and then you check that it satisfies the cocycle condition. And in the other direction, it's even easier than in the field case, because I don't need the shift to be representable here. So there is no, well, the descent result you use is much easier. So the two H1s are the same. So we can talk about torsors or about cocycles. Great. So now, yes, maybe just mention one theorem to be reassured about the object we are dealing with. So if curly J is represented by an affine group scheme, over S, then all torsors are representable. So they all are really schemes. All S torsors are representable.
It's represented by a group scheme, right?
Yeah, this is what I mean here.
Oh, sorry. Yeah.
When I say G is a group scheme, I mean G is representable by a group scheme. Okay. This is just a consequence of FPPF descent, if you know it. So this is just to be sure that in the applications to local global principle, we will only deal with varieties in the end. Okay. But for the general definition, we don't need this representability. So the proof is just FPPF descent. So now I have to define the so-called twists that I mentioned before. So twists. So first, let me mention that if Y and P are torsors, so let's say Y is a left and P is a right torsor, so S torsor under G. Then the automorphism sheaf of the torsors. So by this I mean exactly morphism of torsors from Y to Y. Okay. So this is a sheaf in groups. So anyway, this is it is a scheme in this setting, but in general this is just a sheaf in groups, and this is a group that is locally isomorphic to G. This is the form of this group, but not, it is in general not globally isomorphic to this one. Okay, so I will denote it by G twisted by Y, because, no, the G is like this, sorry. And I will denote with a similar notation the twist of the automorphism group of P. This will be just say G twisted by P, so I just have to choose a notation like this, P below and here Y above, just to distinguish between left and right. Okay, so I will need this notation later. So just keep in mind that these groups are, so if you are over a field, the automorphism group of a torsor is just an algebraic group that becomes isomorphic to G over the algebraic closure, but not over the base field in general. Okay. And with this notation, I can consider the following definition. So same context. So Y is a left torsor and P is a right torsor under the same group. The contractic product of Y and P, so Y is on the, of P and Y maybe, of P and Y, is the following sheaf. So you take P, so we will denote it by P, well, contractive product with, so we can put some G to keep it in mind here, and so P contracted with Y. The product here is just, you take the product of the two sheaves, and you mod out by some diagonal action of G on both P and Y, defined like, where the action is defined. The action is defined by, so if I write it on the left, and P is a right torsor, okay, so you take a point P and a point Y here, and you define this action, this diagonal action, to be the one you can imagine. Just be careful about left and right. So G times Y, and here P times G minus 1. Okay, G acts on both sides, and you can mod out by the diagonal action, like this. So we don't need to care about the representability of this object, because as a sheaf it is perfectly well defined. And what is interesting is that, so we define it like this, and then this object is itself a torsor. So maybe I will write it here. P contractive product with Y is a left, left and right torsor under. So on the left, so you want to act on the left on P, okay? But G acts on the right on P and not on the left. And in fact, there is an action on the left, not by G, but by the automorphism group of P. So you have two actions on a torsor. You have the action of the group, G, and the action of the automorphism group. And one is on the left and one is on the right. Since here we mod it out by the action on the right, by this action here, we only have left, the action on the left. Okay? So this is a left torsor under this twisted group here. And with the symmetric reasoning, you get a right action by the automorphism group of Y, which was called YG. Okay? So in some sense, we have a kind of product on the set of torsors, but the problem of this product is that we change the group. Okay? The result of the product is not a torsor under G anymore, but under a twisted version of this group. Okay? Maybe a little remark. So a few remarks. If the group is abelian, commutative, then in fact, so here you can see this twist as a twist by inner automorphism. So in fact, this twisted group is isomorphic to G itself. Okay, so in the abelian case, you don't have to worry about this problem of changing the group. If G is commutative, P twisted by G is canonically isomorphic to G. And same in the other direction. And this is why we have an abelian group structure on the set of torsors when the group is abelian. The group structure that you can see at the level of cocycles, in fact, you can see it geometrically as a contractic product. Because you take two torsors under an abelian group, and you recover a torsor under the same group. Okay, this is a group structure on H1. But unfortunately, in the non-commutative case, the set of G torsors is not stable by this product. Okay, and second remark. In fact, you can replace in this construction, you can replace, for instance, Y or P by something with a G action, which is not necessarily a torsor. To define the contractic product, you just need that the action is defined. And in order to have, you won't recover necessarily a torsor here, but you will recover a sheaf with an action of a certain group. And it will be useful in the following. So if Y or P is just a sheaf with an action of G, we can define a similar twisted, a similar contractic product, which will still have nice properties. We can still define the sheaf. P contractic product with Y, just as a quotient, diagonal quotient, and it will be useful in a moment. Okay, so this is the operation. Yes, and the third remark. Sorry, there is a third one. So this operation is a bit strange because this is not symmetric. The group action is on the left on one side and on the right on the other side. And I define H1 as this set of isomorphism classes of one kind of torsor, say a right torsor. So if P and Y are both right torsors, well, there is a way to transform a right torsor into a left torsor, just by acting by G inverse instead of acting by G. Define Y0 to be the opposite torsor, the left torsor associated to Y. So I don't define it precisely, but just instead of acting on the right by little g, you act on the left by little g minus 1. So this is the same action, but just with a minus 1, which transform right to left. And then you can define the twist. And this notation will be very useful in the following. So the twist of p by y will just be the contractic product of p by y inverse, the opposite. Now, this makes sense because p is a right torsor and y0 is a left torsor, so you can contract them into something that we call p twisted by y. The interest of this operation is that the input were two right torsors, so two elements in the same H1. Okay? So we will need this before. And we call this the twist. The twist of p by y. And we want to understand this as something that is locally isomorphic to p, but not globally. As soon as y is trivial, this one is isomorphic to p. Okay? This is why we call this a twist. Okay.
Is there a relation between this thing and if you change p and y? You say it's not symmetric, right?
Yes, it's not symmetric, but here, here it will be. So what can we say about this one? Yes, this one is following what we wrote there, is a left torsor under G twisted by P, and is a right torsor under G twisted by Y or Y0, okay? And if you exchange Y and P, you will get something that is a torsor, which is a left torsor under G twisted by Y and a right torsor under G twisted by P. And in fact, when you have such an object that is a bitorsor, so a torsor on the left by something and on the right by something else, you have the similar operation 0 here that exchange left and right. So the conclusion is that P twisted by Y is the opposite of Y twisted by P for this definition. So it's almost symmetric up to sign in some sense. Okay? Okay, so now we have this notion of twisting a torsor by another one. And now we can give the idea of descent, so 3.2. The idea of descent. So we want to define something called the descent obstruction to the local global principle. So let me give you an idea of a geometric idea of how it works. So we fix K a number field and X a nice variety. So here nice means as before smooth projective geometrically integral. Well, in fact it's you can weaken the assumption, but it's not important to give the general idea. So the idea is the following. Yeah. Instead of only looking at what happens on the variety X itself and involving Brahmanian obstructions and all kinds of things, but related to X itself, the broad group of X, and everything is defined over X, we can look at what happened to a big family of varieties over X. So we will consider a family of varieties over X, and in particular, torsors. Let's say this will be a torsor under. So you fix a torsor. So let's call F this map. Let Y to X be a X torsor under a linear algebraic. Linear is not necessary here, but let's say linear algebraic group J over K. So here I will only consider X groups that comes from the field K, so constant X groups. So for instance, GLN, PGLN, and so on. So you take a constant X group, K group, you take a K group, and you extend it to X by the structure morphism, so you get a group scheme over X, and you can consider torsors under this group scheme, okay? So you fix such a torsor, and the idea is that even though, well, looking at the local global principles on obstructions on X, in general won't be enough, but if we look at local global principle on Y, for huge collections of torsors Y, it will give a more precise information than what happened on X, okay? And let's try to make a precise statement of what I just said. Yes. Now if we take a rational point on X, so take a rational point on X, let X be a rational point. Then I claim that this point almost lift to Y. Almost. This is not true, of course, in general, but then there exists a cocycle, say sigma, a Galois cocycle for the group, for the algebra group G here, such that X lift to not to Y itself, but to the twist of Y. So this cocycle corresponds to a torsor over K. You can pull back to a torsor over X and twist in the sense we defined before. You can twist this torsor by this one. You get a new variety over X, which is itself a torsor under G sigma, a twisted version of G. And what I claim is that you can lift your rational point to a twist of this given torsor here. Why is it true? This is essentially obvious when you write down the things, everything. Indeed. So you can consider the fiber of f at x. Let's call it f minus 1 of x, or y sub x. So this fiber, by definition of a torsor, the fiber of a torsor is still a torsor under the fiber of the group, okay? Which just means that you can pull back torsors by a map from Z to X. You can pull back a torsor to get a torsor of a Z. And so here, you see the rational point as a map from spec K to X, and you pull back. So you recover a torsor under G, in fact, because since G is constant, here it was the group scheme GX, and you restrict it to a fiber, you recover the G you started from. So this one is a K torsor under G. And I will twist. The idea is this one will be the sigma I'm looking for. Okay? So now you just consider then this is just a simple verification to check that when you twist when you twist Y, this big torsor here, by the fiber, okay? By this I mean exactly, you take the fiber, which is over spec K, and then you extend it to X. You have two torsor over X, and you consider the twist. Okay? this one, which is defined by something like this, okay? It has, so this one is the torsor over X. You can take the fiber of a, so this is the torsor of a capital X. You can take the fiber at X, and everything is defined so that you get something that is isomorphic to Yx twisted by itself. And when you twist a torsor by itself, you just have to follow the definition. But this torsor has a natural rational point. So this has a rational point. This is essentially tautological once you write the definition of the twist of a torsor by itself. And it exactly means that, well, since this fiber has a rational point, it exactly means that Y twisted by that X lifts to the twist, okay? Just put sigma to be Yx. Sigma equals the class of the torsor Yx works and satisfies this condition. Okay, so any rational point, given any torsor, a rational point always lifts to a twist of this torsor. Okay? Now what happened for adelic points? Okay? So to summarize, so as a consequence, we have the following equality. Well, this is an inclusion. This is an equality, in fact. A rational points can be written as the union over all cohomological classes for this given G here of the image of the twist. So I just proved that any point here lifts to some twist. So it proves the inclusion of the left into the right.
Well, you don't know if it's unique, right?
It doesn't seem to be unique, but in fact it is. So this is a disjoint union. In fact, you have to choose the fiber to get a rational point. If you choose something else, something that is not isomorphic to the fiber, then you have no rational point. You have to check it, but so this is really a disjoint union. So this is a partition of the set of rational points given by a torsor. Okay, disjoint union.
Maybe we could say that
yeah.
the sigma that you get is just the evaluation of the class of the torsor.
Exactly. Exactly. So this is the geometric description, but we have a more I don't know if it's more concrete or not, but a more cohomological description. Equivalently, let's write it on the other blackboard. No, I should not do this. Oh, yes, this works. Yes, so as David says, there is a in fact, taking the fiber of a torsor can be rewritten as taking as a map in Étale and Galois cohomology. So, remark. So the map from H1 of X, G to. So you fix X. X is given in the set of rational points. So you have this X of a star map. Okay? And if you consider a torsor here, as we did before, the map, given the pullback map given by the rational point, corresponds exactly to taking the fiber. Geometrically, it corresponds exactly to taking the fiber. Okay? So this is a cohomological description of the operation we did there. And using this description, you can recover that the only way to twist y so that it becomes trivial here is to twist it by its image. Okay? If you twist by something else, here you get you get something that is not equal to this one. That is not trivial, sorry. Yeah. So this, the pullback mark exactly corresponds to taking the fibers. Okay. So you see this equality over there? Now we try to look at what happens for adelic points, because this is what we are interested in. So now, if you consider an adelic point on on X, sorry, you can compare this, the set of adelic points, with the set of well, you take the similar set on the right, but you put adelic points instead of rational points, okay? Okay, I just put the same set as above, but I put adelic points here instead of rational points, okay? Then you can define this, okay, this makes sense. By functoriality, of course, a point here is an adelic point in this set, okay? But this is not an equality in general, because if you choose a point here, and if you try to apply the same machinery as we did before, you should twist f not by a global cocycle, but by an adelic cocycle, the collection of fibers of your torsor above your adelic point. But here I really want to twist by a global class, okay? So here I keep the global class here. So we have an inclusion there, and by the equality above, of course this one contains the same union with the k here, so it contains rational points, right? So here we have a candidate to be an obstruction to the Hasse principle, because it is contained in adelic points and it contains rational points, right? So we will denote this one by x ak obstructed by f, or unobstructed by f. So the element, the adelic points of x that survive, in some sense, the torsor y, that can be lifted to some global twist of the torsor y, okay? So we will denote it by xa to the f, torsor f. Okay. And now that I define this, I can go to, I can compare this kind of obstruction with a, okay, yes. So this is 3.3, I think. So this is basically the idea. So you define an obstruction using a torsor. And now we try to compare descent obstruction versus Brouwer-Manin obstruction. So recall that we had two ways of defining the Brouwer group of a scheme. Either by étale cohomology of GM, blah, blah, blah. Or we have a definition by central simple algebras over X, over the scheme, so-called Azumaya algebra over X, that we can define. So I don't have the time to define it precisely, but we can define another Brouwer group, not the cohomological one, but the Azumaya Brouwer group of a variety, of a scheme more generally. as a set of equivalence classes of so-called Azumaya algebras over X. And you should think of Azumaya algebras over X as some shiftified versions of a central simple algebra over a field. Okay? So in particular, in Azumaya algebra is a over X is just an algebra that is locally isomorphic to a matrix algebra over X. Is locally isomorphic to the algebra of this shape, Mn of X.
Locally in étal.
Étal, yes. You're right. Let's say étal. Okay, so this is just some what we could call a form of X of this étal algebra, of this Azumaya algebra. And since the automorphism group of the algebra, of the matrix algebra, so if you believe that it works the same as over a field, for instance, so the automorphism group of a matrix algebra over a field, all such automorphisms are inner automorphisms. So they are given by GLN modulo the center, so by PGLN. In fact, this is, you can generalize this isomorphism over a scheme. So you get that the automorphism of this matrix algebra, so the sheaf of automorphism is exactly the group scheme represented by PGLN. Over a field is somehow classical, but it works over an arbitrary scheme. So you have an action of PGLN on this algebra, and an Azumaya algebra is just something that is locally isomorphic to this one. So if you come back to this notion of twist by a torsor, if you twist this trivial algebra by a PGLN torsor, you will get something that in the end is locally isomorphic to Mn of Ox. Okay, so something that looks like an Azumaya algebra. And in fact, this is exactly an Azumaya algebra, and all Azumaya algebra I obtain as twists of Mn of Ox by a PGLN torsor. So you get, so this is, I'm going too quickly, but you have to explain how to twist an Azumaya algebra by a PGLN torsor. I explained how to twist torsors. I said in a remark there that you could twist other things. So for instance, you can twist a vector bundle by a torsor under its automorphism group and so on. You can twist a line bundle, a trivial line bundle, you can twist it by a GM torsor and so on. So this is a general, you can twist a lot of things and you get a bijection between each one of X PGLN. Now this classifies X torsor under PGLN, okay? And in the other direction, isomorphism classes of Azumaya algebras of rank n squared, which are locally isomorphic to Mn of Ox. Okay, so you get a bijection between these two sets. So that's why we said that Azumaya algebra of rank n squared are classified by this set. So they are up to isomorphisms that are the same as a PGLN torsor over X. And the operation is just given a torsor, you can twist the trivial algebra PGLN twist by this torsor, whatever. Well, I did not define exactly what this means, but in fact you can glue trivial algebras along the torsor, along trivialization of the torsor P. And in the other direction, it's easier to understand, because given an Azumaya algebra, you can look at the sheaf of isomorphisms between this algebra and OX. Well, I'm not sure if you should, maybe you should change if you want the torsor in the correct, on the correct side, but anyway, it's not very important. So either this way or the other way around. And this one is a torsor on a PGLN, canonically, because PGLN act on this side. Sorry, this is, sorry, Mn of OX, sorry. Sorry, yeah. Okay, so this is a bijection. And why is it interesting in terms of obstructions? Because on this side you have something related to the Brauer group, and on this side you have something related to torsors. So descent obstruction, Brauer-Manin obstruction. Okay, and yeah. So in addition, consider the exact sequence. So if you consider the exact sequence GM, GLN, PGLN over X, okay, everyone believes that this is an exact sequence, and of group schemes, so of FPPF sheaves, if you want really to give a sense of surjectivity of this map, then you get a co-boundary map, or boundary map, I don't know. So this is not a sequence of commutative algebraic groups or commutative group schemes, so you have to be a little careful. But you get a map from H1 to H2. Okay. So here you can put et al. And this is the usual cohomological Brauer group here. Okay. And here, this is related to the Azumaya Brauer group, because this is related to Azumaya algebras. So from this map, taking in some sense the limit over all n, this implies the existence of a natural map, which is a natural map which is injective in general from the Azumaya Brauer group to the cohomological Brauer group. Okay? To define this map, you have to pass to PGLN torsors and then apply the co-boundary map. So this is defined. It's quite easy to define using Čech cocycles. Okay? Because H1 is the same as H1 Čech. Here you have cocycles, and you define here an obstruction to lift this cocycle to a cocycle here. Okay? There is a nicer definition of this map using gerbs. And the description of this one, not as cocycles, but as a set of equivalence classes of gerbs, but it's more technical to define this object. So we will just use the cocyclic definition. So you have a map, and as David says in his talk, for a nice variety of a scheme, say a quasi-projective variety over a scheme, quasi-projective, say smooth variety over a scheme, this is an isomorphism. Isomorphism if X is, say, smooth and quasi-projective. This is a deep result by Gaber. Okay? But why is it interesting for us? Because it's a way to relate cohomological Brauer-Manin obstruction to Azumaya obstruction, hence descent obstruction. So let's give a theorem.
So it's maybe no question. Can you just comment on why
definition on isometric algebras is not literally isomorphous from y to
Yeah.
two equivalent isometric algebras go to the same.
Yeah. Yeah. You're right. You have to check something here. This is not so obvious. I mean, if you have the here, etal is here. So you have to check that if you take the delta of say A tons of B, in some sense you get the sum of the deltas of A and delta of B, which is not very easy to check at cocycle level. You can do it, but it's not very obvious. In fact, if you take here the definition with jobs, you just map a torsor here to the jobs of liftings to a torsor here, and then it is clear that it will be compatible with everything. But the definition with cocycle, it's much more difficult to check that it. In fact, Mills in his book, Mills just say that this is true, but he doesn't prove the formula. So yes, there is a compatibility formula to prove before passing from this line to this line. You're right. So theorem. What was I saying? Yes. So let's put the name of maybe Harari and Skorobogatov. So two statements. The first one is I didn't define. Maybe I can define it after the result. So I define x ak. So here x will be, so k is a number field and a is a smooth and quasi-projective variety. And I define x of ak PGL to be the union over all n of the union over all PGLN torsors over X of the sets. This should be intersections, right? So you will take points in X that survive any PGLN torsors for any n. And here you put the descent subset that we defined before. Okay? So these are really adelic points that survive, that can be lifted to any PGLN torsor up to some twist for any n. Okay? So this is a descent obstruction associated to the group PGLN. And what they proved is that this set is exactly the Brouwer-Manin set. And there is then a result by Harari which proves that if you put here not only the group PGLN but any linear connected, so I will put here connected, then you get no more than the Brouwer-Manin obstruction. So I have to define this connected descent obstruction. This is just, well, you take the same definition, but you replace PGLN by any linear connected algebraic group. And XAK connected is just, you take any G, so any torsor from Y under G, any torsor from Y to X under G, where G over K is linear and connected algebraic group, so usual algebraic groups, and you take the intersection of all the descent subset. So taking descent obstructions for any linear connected algebraic group gives exactly the Brouwer-Manin obstruction. So no more. So we didn't refine the Brouwer-Manin obstruction this way. But as you probably know, all algebraic groups are not connected. So So we could consider non-connected algebraic groups. So this is the last section, so 3.4. Stronger obstructions. More precise obstructions. So the idea is to define the following set. The so-called descent obstruction set, which is the same definition as the connected, but you remove the connected assumption, okay? So you take any torsor on the G. G is just supposed to be linear. And you take all these sets. So in some sense, you are looking at instead of looking just at adelic points over X, you are looking at the existence of adelic points over any torsor over X. So, and this obstruction will be strictly stronger than the Brownian obstruction. And you can define another, you can try to refine the Brownian obstruction in another direction, which is, you can try to put here something called Étale-Brouwer. And what does it mean? You consider any finite, so F here is a finite algebraic group over K. So the groups are always over K, right? The groups are always over K. You take here not all linear algebraic groups, but only finite étale covers of X. And you put here, instead of looking at all adelic points, or instead of looking at all adelic points on the torsor, you look at all adelic points, only at adelic points that satisfy the Brouwer-Manin obstruction above. Okay? And one more time, this set here contains rational points by the same kind of argument as we did for the descent set. Okay, so this is called the Étale-Brouwer-Manin obstruction. So this is descent obstruction to the Hasse principle, and this is called the okay. The last one is called Étale-Brouwer-Manin obstruction. The last one is called Étale-Brouwer-Manin obstruction. So of course these sets are in general less computable than the Brouwer-Manin set, because you have to take into account all these torsors. But we have some nice theoretical results about them. So let me state this result to finish the lecture. So the first for the first example where these obstructions were used is the example by Skorobogatov in 1999, where he proved, so he constructed this variety for which I already mentioned, which had adelic points orthogonal to the Brouwer group, but no rational point. And what he proved, in fact, what he proved is that it had no adelic points satisfying the Étale-Brouwer condition. So this stronger obstruction here, so it proved that this obstruction is stronger than the Brouwer-Manin obstruction itself, strictly stronger. And in this example, you can explain the failure of the Hasse principle, not by the Brouwer-Manin obstruction, but by this Étale-Brouwer obstruction. Okay? And a few years later, Harari and Skorobogatov also proved that in this example, the descent obstruction the descent set was empty. So both obstructions here can explain the counterexample by Skorobogatov. So here, this one was quite, so the variety X was constructed as a quotient by Z mod 2 of a product of genus 1 curves. Okay, you take two genus 1 curve, you take the quotient by an involution, and you get this X. So you have a natural torsor, a Z mod 2 torsor above your X, and using this Z mod 2 torsor, Skorobogatov proved that the Étale-Bauermann inset was empty, which means that any adelic, an adelic point cannot be, there are no adelic points that could be lifted to the product of genus 1 curve that he defined, okay, even up to twist. And here, they had to use a finite non-abelian group of order 32, if I'm correct, and a torsor under this group of X that has no adelic points, even up to twist. Okay, so the example of Skorobogatov is explained by these two stronger obstructions. Unfortunately, Poonen, in 2010, I think, produced another example over any number field of dimension, so a nice variety of dimension 3, for which the Étale-Bauermann inset is non-empty. So it seems that the stronger obstruction we could define doesn't see, well, always see nice adelic points, but there are no rational points. So even though this obstruction is more general than the Bauermann obstruction, it's not general enough to explain this counterexample. Okay? Yeah, maybe I mentioned last result and I stop. I mentioned a last result due to several people. Say Sao, Yang Sao, myself, Skorobogatov, and Shufei in 2000, well, for many years, during several years, we proved that, in fact, for any nice variety X, these two obstructions are the same. So the descent and the Étale-Bauer one are the same. So that's where we are now. So we have these stronger obstructions defined by descent theory, which are strictly stronger, as this example proves, which are strictly stronger than the Bauermann obstruction, which are really nice refinement of the Bauermann obstruction, but they are equivalent, so in fact they are the same one. And Poonen example showed that the story is not over. And we have no other candidate. I think we have no nice candidate to be more general than this obstruction sets. There was an attempt by Arpaz and Schlank to define another obstruction using Étale homotopy theory. But in the end, what they prove is that they recover exactly the same as these ones. So this is the conclusion of my talks. Thank you.